Now the question is, prove that if A, B and C are random events in a sample space and A, B, C are pairwise independent. So if they are pairwise independent, then P A intersection B is P A into PB. P B intersection C is PB into PC. And P C intersection A is PC into PA. And A is independent of B union C. We are given that P A intersection of B union C is probability of A into probability of B union C. Now we need to prove that A, B and C are mutually independent. That means we need to prove that probability of A intersection B intersection C is PA into PB into PC. Now first we look at this P A intersection B union C. So probability of A intersection B union C. Now if we look at the Venn diagram, now suppose this is A, this is B and this is C. Now it says A intersection B union C. That means that portion of A which is common with either B or C. That means we are talking about this region. So this P A intersection B union C, it is actually equal to probability of A intersection B plus probability of A intersection C, and since we have taken this region twice, so it will be this minus probability of A intersection B intersection C. Now we can write this as probability of A into probability of B plus probability of A into probability of C minus probability of A intersection B intersection C. Now we are given that it is equal to PA into P B union C. So it is equal to PA into P B union C, and B union C is PB plus PC minus PB intersection C. So we can write this as PA into PB plus PC minus P B intersection C, which is equal to PAPB plus PAPC minus PA, and since B and C are also independent, so it will be this PB into PC. Now PAPB will cancel and PAPC will also cancel. So from here we get this result that P A intersection B intersection C, it is equal to PA into PB into PC, which is what we need to prove in this question. So we have proved that A, B and C are mutually independent. Now in the part B it says an event A is known to be independent of the events B, B union C and B intersection C. Show that it is also independent of C. Now A is independent with B, that means P A intersection B is PA into PB. Now it is also independent with B union C. So A intersection B union C, it is equal to probability of A into probability of B union C, and also it is independent to B intersection C. So from here we can say this is PA into P B intersection C. Now again we'll simplify this. Now this is probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection C, and it is equal to PA into P B union C, and we can write B union C as probability of B plus probability of C minus probability of B intersection C. So this is probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection C, and it is equal to PA PB plus probability of A into probability of C minus probability of A into probability of B intersection C. Now P intersection B is PA into PB, will cancel, and PA intersection B intersection C is PA into PB intersection C, so it will cancel. So from here we get this condition that probability of A intersection C is equal to probability of A into probability of C. That means events A and C, they are independent, and that's our second part.